Yeah, so that's why when I entered the room, we had like a confused look in a lot of people's faces that, hey, this is supposed to be a woman, so what is he doing here? So yeah, so she's out, but it's not like they met someone in an elevator and said that, hey, why don't you just go and present and P and SQC? So it's not that. I am also a co-author for this paper, so I hope I can do justice to this presentation. So just to have a estimate of the audience, how many of you are project managers or program managers? Oh, awesome. So a couple of them. So it's really good. So this particular work that we did, so this uses defects, and so we built a prediction model, and it'll help us in estimating the project schedule. So what do I mean by that is, see, I mean, most of the time, so whoever is wants a product out in the market, so most of the time what happens is it's more focused on how the customer wants to buy. So if it's a holiday refresh cycle, or say the fall season where everyone's going to school, so the timelines are more dependent on that. So you don't focus on, hey, how much time does it take to develop something? How much time does it take to test something? But you want products out on time, but you don't know what's the quality of those products. And a lot of times customers come back to us and say, hey, you're not doing a great job. So I know you want to release your product, but ensure that it's top-notch quality. So that is the problem that we are trying to address over here. So let's begin. I'm Debashish. I joined Intel fairly recently, and I think I have the least amount of experience amongst all the speakers over here. I think I have 4 years of software engineering experience. I don't know. That's good enough. So, but yeah. So I have a master's degree from UC Santa Barbara in electrical and computer engineering, where I did a bit of machine learning and computer vision. So that's about me. So let's get started. Hope you guys are relaxed and awake. So yeah. So yeah, bugs, as you see, are everywhere. Whether you like it or you don't like it, probably testers like it because they love to report it. Because I mean, it shows that they're doing the job pretty well. So, but developers hate it, and to be honest, everyone hates it, some kind of the other. So there was a survey conducted by System Sciences Institute at IBM, saying that the cost to fix a bug increases exponentially, and it goes up to 100 times as what it was initially. So say for example, you guys, any of you guys have installed the application Pokemon Go? Oh, really? Awesome. So how many of you did that on the first day, or first few weeks, or first few days? No one? Oh, okay, awesome. One really diehard fan of Pokemon Go. So if you would have noticed in that application, there was a small bug. Probably you wouldn't have noticed, because I think that's the biggest lie if you say that when you check the mark, I have read and accepted all the terms and conditions. So I don't think everyone reads that, or anyone, to be honest, reads that. So you basically check it anyway. So what it actually did was, the app, so you had to, if you were to log in using your Google account, you were basically giving full access permissions. Yes, that was a bug. That was a major bug in Pokemon Go app, but I mean, they later came up with a patch and said that, hey, we didn't use anything. We did did have access to your data, but we didn't do it. So they gave a confirmation from Google, and so I think that's pretty much it. And so that was not that bad of an example, so because nothing happened. But say for example, the recent exploding Note 7 batteries. So it has $17 billion in shares that were lost in 1 day when they stopped, and they said that we don't want it. So why do you think that Samsung is so just because of one small case, now it's all reputation is under question. So the thing is that we need to address this thing, no matter what, we shouldn't ship out products by knowing that we are going to ship out with so-and-so bugs. So that is the problem that we are going to tackle, which leads me to the problem statement. So the biggest statement is, the question is how do we estimate the total number of defects in a particular project? So everyone wants to know it. If suppose you by chance know the future that, hey, this product is going to have these many defects, so you're going to say that, oh, okay, I'm going to do a lot of testing in this period of time so that I ship the product to a customer or to the end user saying that, hey, this product is really good, you don't have to focus much on that. Secondly is like, how do we define project milestones? Like I said earlier, that most of these project milestones are dependent on the customer. Like, when do they want the product? So when do people want to buy it? So we don't have anything as such. How do you know that whether your alpha or your BT or your production release qualification is planned way too early or way too late? You don't know that. You just base it on like previous past projects, like, hey, I shipped it at this time, so it may work for this thing, so I have a 1-year time period. That's not how it works. So we need to really take this into consideration of like having all the milestones planned accordingly. So our ultimate goal is to have the utmost quality of a product. So that brings us to our proposal. So this is the work that we did. We built a prediction model. So this will help us in scheduling project milestones, identifying and evaluating the risk in existing program schedule. So what I mean by this is that if it's an ongoing project and you want to know like how many defects are going to go after you release, so that is how you estimate the risk, and then you evaluate accordingly. And so third thing is that we're doing monitoring of in-process quality of product. So this is regularly implemented across various projects. So we also take preventive actions so that, hey, we don't know something's going to happen at any time. So we have to ensure that we are able to commit to that and also take preventive actions. And also, this is the most important, like, how do we meet time to market needs? So that is what we are proposing. So to begin with, like, how did we even come across this thing? How did we even start building this prediction model? So here is starting prerequisites that you would need. So first thing is historical defect data. Historical data is like really precious, so never ever lose track of it or just say that, hey, I'm not going to use this again. So take a note of that. Second thing is we need a track of all major milestones. Not everything is required, but the major ones like alpha, beta, or the production release qualification. So we have taken those three into consideration. So it's up to you. So whichever milestones you want, just keep track of it. So third thing is, in the historical defect data, we are only considering the defect dates. So what defects were logged at what time or what dates, to be specific. So why we are doing that is we don't want our system to be overburdened with a lot of factors, like whether it was a high priority defect, critical defect, so we are considering everything. We are taking everything, all the defects, and we're just considering the date and the count. So in past, we have been using some bug tracking systems like Jira and Bugzilla across Intel, and so like just dig in and just plug in all those database results. So you have like a list of these details. So here I'm talking about some major project milestones. So this is like a very like a basic way of saying, like, I'm not going to go into details like what exactly alpha criteria or beta criteria are. So with respect to defect prediction, this is what we are expecting. By the time we hit alpha, we expect around 50% of the defects to be completely resolved by that time. By beta, we say that, okay, so validation was pending, so we are completing validation, so we expect to hit around 70% or 60% of the defects. So same thing goes with PRQ, which is the final release. So we expect, like, we want it to be 100%, but we know that it's not going to be. So we expect around 70 to 80% of the defects being resolved by this time. So this is our benchmark. Like, we want this to happen in all our projects. So having said that, let's begin by just plotting some data and observing the trend. So like I said, what we need is the work weeks and the defect count. So for example, in this table, so 2013 work week 38, so we had one defect. And in 39, work week 39, we didn't have any defect, so the cumulative became 1. Similarly, if you go on like work week 41, it's 3. That means in work week 41, you had 2 defects. So it's been added up. And as you see, it went up to 3,500 defects. So this is what happens in a project. Like initially, nothing much. You don't see many defects coming in, but in the end, it increases exponentially. So when you plot this two-dimensionally with work week on your x-axis and cumulative distribution defects on your y-axis, you are going to see this trend. So there's a question to you, like, do you see any patterns in this? So, nice SCurve. Yeah, exactly. So this resembles an SCurve. So like the next question is going to be, what's next? What do you do with this? So I hope this is not the boring part. You build a mathematical model out of it. You have to. I mean, this is a place where we have to involve math in us. So I'm just giving a brief overview of what an SCurve looks like. So this is a sigmoidal function. So this is a very basic one, which is given by this equation, 1 divided by 1 plus exponent of negative of x. So in this particular sigmoidal function, you cannot do much. You don't have much liberty of changing the s, the length or breadth, or even the steepness. So that's why we want that functionality as well. So we are using a more generic version of that s. So that is a logistic function. So what it does is it gives you more range over the amplitude, the steepness, and the length of that s. So why are we doing that is going to be displayed over here. So let's apply that to our defect trends and see how it trends. So this was our s that we just plotted, and when we actually use this logistic regression, we are seeing that the curve fit is almost perfect. So we are using R-square regression, and for that, these parameters, so the equation that you're seeing over here, the cumulative defects with respect to work week is nothing but just the same representation of logistic regression function, but those are more, I mean, the parameters make more sense to us in the sense like asymptote, when I talk about asymptote, it's nothing but the total number of defects. So it's the peak at which, so when we saw 3,500 defects, so my asymptote was 3,500. And when I talk about growth rate talks about how fast or how slow my defects grow with respect to a project. So if a project is, say, very like, say, a 1-year time span, and you have a lot of developers, validation engineers working on it, you will see a lot of defects coming out of that project. And similarly, if it's a more stretched out project with lesser number of resources, then you'll see lesser growth rate, lesser trend. And third parameter is the inflection point. So inflection point is the work week at which we see 50% of the defects. So when you talk about 3,500 defects as your asymptote, the work week at which you see 1,750 defects is your inflection point. So we need these 3 parameters to replicate our S-curve. So that is why we built a mathematical model, and this is how it is done. And so we have used an inbuilt tool, like we had jump provided by SAS. So it already has these functionalities. We just have to use it. So if not, we can always write a piece of code. It's just scripting. It's not that big of a deal in this. So what if we take a not so perfect data? So what I mean by that is we just took a normal S, but we know like a lot of projects don't behave that way. For example, you have a Christmas break or you have a New Year. So there are a lot of people going on vacations, and no one's going to test, no one is going to develop any code in that. So what happens is a lot of places you will find that, hey, my curve is not going as I predicted it to go. So what happens is that time. So we still apply this model and we still get a pretty good accuracy. So what this does is that when you have this mathematical term called R-square, where it actually fits the curve closer to this thing, and the error rate is very less. So yes, this works. So we've tried it for like bunch of different projects, and yes, it works. So to address the elephant in the room, can we use this model for prediction? Well, the answer has to be yes. If not, I wouldn't have been presenting here. So this is a flowchart of how we are going to achieve that. There are 5 steps to it. The first step, which I already talked about, is using those, getting the parameters from the database of previous projects. So in that sense, say you want to predict for a new project, say project X, and you have data from its previous project. So what you're going to do is you're going to populate that using jump, or you can write your own regression. And you will find those 3 parameters over here, which is illustrated in that oval, which is growth rate, inflection point, and asymptote. And once you have a set of all these parameters, then you go to step 2, which is you're discussing those parameters with certain dependencies. What I mean by this is that every project has certain number of components. So you have to discuss more on the architectural complexity. You have to discuss about the number of features, how many validation engineers were there. So all these parameters, and I have slides on this as well. So I'm just giving you an overview of what this is. So based on this, you're going to discuss those parameters, the ones which you got over here, against those dependencies. So once you have a brief overview of what went on in the project, and then you do the step 3, which is to estimate the delta to future project. So in this case, so for a new project, which was, say, an additional feature of a previous one, so then you will try to correlate this with those dependencies and apply certain like techniques where you estimate that there is a 10% increase or a 20% increase, and then you finally figure out and say that, hey, this is my final estimate. So once you have that estimate, so you'll plot it in, and because this is a completely new project, say it's 1 year down the line, you just have a trend, and then you plug in your future milestones, and then you see whether those milestones are actually syncing up with your expectations. So say, for example, you planned that next fall, say October, before people go to school, I want my PRQ. So when you plot it, you will see that, hey, no, this is not something which I want. I'm going to see like so-and-so X amount of defects after that. So what should I do about that? Which leads us to step 5, where you have discussions with your program manager, project managers, all the architects, and say that, hey, if you do that, we are going to see these many issues. So let's take a closer look at each of these steps. So first is to generate reference parameters from past projects. Like I said, we are using jump, but you're free to develop any sort of regression technique, so as long as it is logistic 3P. So since we're using jump, it's more of plug and play. So in the first step, you have the data table of all the work weeks with respect to the defects. Second step, you say that you're using a nonlinear model. Third step, you say you define all the parameters where x-axis and y-axis are, which is your cumulative defects and work weeks. Your fourth step is your actual plot, as you can see over here, the dotted lines. And fifth step is to fit this using a logistic curve. And I'm not sure, yeah, I think it's visible, but I'm not sure, like the green line or some line which actually fits that curve. So, and you see those parameters over here, the growth rate, inflection point. It's a little blurred, but that is where you're going to get all these parameters. So once you generate all these parameters, so this is an example of, say, 3 projects, A, B, C. And these are actually real world projects. I just masked the names because it's Intel. So, and once you have that, this is a tabular form where you actually generated all those parameters. And as you see in these projects, the final release was somewhere over here. If you expect around 30,000 defects, you shipped it to a customer with 15,000 defects. So and in this case as well. So this is something that we want to avoid in future projects. So yeah, one thing also we noticed that in this case, growth rates are quite similar. So moving on, so once we have those parameters, we discuss those parameters with respect to dependencies. So what dependencies to discuss? So like I said, you need to discuss about architectural complexity, the number of features, number of programmers, development methodology, or verification technology, and project timeline. So who are the right persons to discuss this with? Say the program architect, or the program managers, or the quality engineers who have been in this project for for the last year, or those who were involved with this. So this is where you come up with an assessment. And one thing we need to also consider over here is that we are not quantizing anything. So we are not saying that, hey, this many increase in features leads to this much. So say this is a very vague term, like it's more complex or it's less complex. So it's up to the architect to say the complexity. So if you ask me to differentiate, to say that, hey, one system is more complex than the other, so how much times, or like how complex is it? I won't be able to say it's like 10 times more complex. So this is the answer. This is a question that has to be asked to all the architects. So they they'll be definitely able to assess, saying that, hey, so all these dependencies, they are the best persons to answer. So that leads us to the step 3, which is the delta discussion. So in this case, I'm showing you an example of how we are doing it. So the only cue that I'm giving you guys is that I'm giving you 4 projects which were 1 year long, and I'm giving you the growth rates and inflection point and asymptotes. So my question to you is that, based on just this information, will you be able to predict for a completely new project? So just by this information, you see the growth rate, it goes down from 0.18 way down to 0.04. And then you see inflection point goes from 25 to 78. And over here, you see like 4,000 defects at one point, and you see like 200 defects. So what do you think? Yes, no, maybe, I don't care. So the answer is no, you can't. I think I missed that, yeah. No, you can't. The reason behind this is that I did not give you much information to go on with. Say, if I were to say that, just ignore project C and project D for an instance, and just look at A and B. Now you see that 0.18 and 0.15, just ignore 0.04 for a second, and 78 and all that stuff. So you see like 3,000 and 4,000 defects. These make more sense to club A and B together. Similarly, just ignore A and B for a second and just look at C and D. So you see 0.04, 0.05, 78, 260, and 300. So this makes more sense. So indeed, this is what happened. A and B are similar. B was derived from A with just an incremental number of features. Same goes for C and D. And C and D were nowhere related to A and B. And the vice versa is true as well. So in this case, what you're going to do is, you're not going to have run this on all the projects across your company and say that, I have this many reference parameters, I'm going to take some average and say that, hey, my new project is going to work like this. So that's not going to happen. So you need to consider the projects that you're trying to predict with its similarities, with the projects that they were similar with. So that is something that we need to keep in mind. So yes, the parameters now make sense. So we were in step 3. So that was a little sidetrack on how we are doing prediction. So this is one such example where we had like 3 projects, and that is what we are estimating. And finally, when we plot it, so the yellow dots, I'm not sure if it's visible to the end. So the yellow dots are the actual trend, and the solid blue line is our prediction. So the actual defects actually follow the predicted trend. So which leads us to the 4th step, which is to put milestones on that and see whether you're doing good or are you in the red zone. So this is, I've taken the same example with the actual defects and the PRQ. So what you're observing over here is that after you ship the product to another customer, or say the end user, you know that there are going to be 8,000 more defects, and you have only, solved only 4,000 defects. That's like 33%, or you're expecting them to do 67% of the work. So this is like an instance of when you're shipping out things when it's like the most buggy state. So what do you do? So this is where you need to have discussions with your project manager, architects, and developers, testers, everyone, and you need to adjust project milestones. So if you were to move this project milestone from work week 36 to say 46 by 20 work weeks, you're going to see a decrease of 4,000 defects. So what I mean by this is that if you had planned this, or if you want to plan it, if you want to move this particular the final release to 20 work weeks later, that's going to do a much better job. That means you're going to solve, or you're going to correct those 4,000 defects during this period, or you can even do further than that. So what I mean by that is you can focus more of the activities in development. So what generally happens in a sprint, or say at the end of a significant milestone, a lot of people tend to focus the last few weeks as their validation sprints, where they test like a lot of things at random, like they have to do it at this time. So instead of doing that, you have to keep planning all these things, all these activities, all the validation activities much more earlier, so that you don't come into this stage. So in this case, this was our only option where we had to move the milestone. But in many cases, when you're like way ahead of time, you need to plan accordingly. You need to rethink at that stage that, hey, I'm going to change it. So now it looks much better, and these are the actual results. So I'm not going to go into much depth over here, but I just want to highlight the point that we observe an accuracy of 80%, sometimes lesser than that as well. So in this case, what we did was, the second column is the actual parameters, and the third column is what we predicted. So we are taking something as a reference, which is the grayed out area. The project A was taken as a reference when you're predicting for project B. So in this case, so what we said was that project A and B were similar architecture, similar timelines, around 1 year as well, and they used the same development and testing methodology, and most of the people were working on that. So the expectation was that we are going to observe lesser number of defects, because most of them have been resolved in the previous iteration as well. So that's why we estimated that this will have roughly about 10% lesser growth rate, 30% lesser defects, and since the project ended much earlier, the way inflection point works is that if the project is smaller, then your inflection point will be much earlier than that, so which is the 50% of the work weeks. So this is based on observation. What we observed after applying this model for a lot of projects, this may not work for you as it is, but you can always apply this to your own projects and come up with these predictions. So similarly, we did the same thing for project C, D, and E. So took C as a reference, and we got similar accuracy. One time it fell down to 80%. Sometimes we observe, say, 60% or 70% of the accuracy, but in that sense, what happens is that you don't know like how close these projects were. So you were just shooting in the dark, saying that, hey, I don't know anything about a project, but what my parameters are going to be. So in that sense, your accuracy is going to fall. So it's always better to have something as a reference. Yeah. So finally, the key takeaways by this presentation was to eliminate the uncertainty in declaring the project milestones. we have achieved in-process quality monitoring of current projects, suggested corrective actions during an ongoing project, and finally delivering the projects on schedule and with utmost quality. So with this, we know that this model is not perfect, it's not complete. So the future work, at least for me, is that to use machine learning to find out patterns, to find out, use others, other than just the defect trends, to understand what went on in the project, to use machine learning and find out all these patterns and then say that I'm going to use something else other than that. So that is something I'm working on. And second is to figure out the other dependencies. Say, for example, you have benchmarking. Say you have, with respect to Intel, if you have the processors, you have the global benchmarking, like one processor is X times faster than the other. So by that, we can cross-correlate and say that, we can come back and say that, okay, so this is this many times more faster. So I can probably correlate that as well. So that is something which I'm working on. And yeah, that's it. And any questions? Yeah, sure.
I have a few questions. I'll let you pick which one you want. I'll list a few questions. You pick one.
I think I'll answer all.
So how do classes of defects affect the estimates? What about team size? And how would you account for something like a company-wide bug bash? Like the whole company comes in and starts generating a pile of bugs. And then how do you account for duplicate bugs? So
Yeah.
which one do you want? Duplicate bugs, company-wide bash, team size, class of defects?
Okay, so I'll first go with the class of defects. So, so what we find, what we did was, in many of the cases, we have separated many defects into high, critical, medium, low. So we try to do our S modeling on each of them as well. So it does work. So, but the problem that you're going to face after that is, you're going to separate that out again, and you need to club it again, and then say that, hey, this is how it trends. But trust me, program managers, project managers don't want to go anything beyond one step. So they just want final saying that I'm going to see these many number of defects. It may include the open defects or duplicate defects or these things, but this is the total count. So say, for example, you have one project where you had a lot of duplicate defects. So chances are that in another project, a new project, there are going to be other duplicate defects as well. So that is what we are taking this thing, so that, okay, so your second question was?
You can just pick one.
Oh, okay.
Take the whole time by saying
Sure, right, yeah.
There's another prediction model like Palic model.
Yes. Yes, we did compare. Yes, we did compare a lot of other models. So in the case where Rayleigh, so I don't know how many people are really familiar with the Rayleigh curve. So it's more of a Gaussian. Okay, so it's a this kind of a curve. So what happens is, in this case, since we are taking cumulative trends, so when you take a Rayleigh function, what happens is, at the time when you hit beta mark or something, when there is a lot of validation going on, you see a lot of peak. So that is where you see a lot of defects. So yes, we did try out Rayleigh and other models as well, but we found the sigmoidal to be the best fit, because you cannot go wrong in this. It has to cumulatively increase. So you will see an S-curve no matter what. But Rayleigh, sometimes you will see all those peaks and then you need to correct it. So yeah, good question, yeah.
How do you account for projects for things other than defects? So budgetary, personnel loss,
Yeah.
holidays, that kind of, large breaks or change in your data.
Yes, so that's a really good question. So I'm not sure if I'm allowed to say this, but I mean, I think everyone knows this, that Intel cut 10% of its workforce. So that means many projects were just canceled, or like a lot of resources were cut. So at that point, I don't think this model is going to work. So it's like these parameters or these factors is something that we cannot like predict. So like after every 10 years, you have a 10% reduction of workforce. So yeah, so this doesn't account for that. Yeah.
You cluster similar projects in groups,
Yes.
like A and B and C and D. for a new project that's coming up, how do you know which group to compare it to? Like,
This
what are
is
your parameters that you look at?
exactly. So this is a really good question. Like, you are developing a new project. You don't know anything about it. It's not even related to any other project. So what are you going to do about it? So you're not going to do any blind prediction. You're not going to shoot in the dark. So, but still you're going to find some project which was similar to that. So by similarity, I mean, you find similarities in the sense that they were similar in timelines, project timelines, or what was the architecture of that, and how do you compare that to some different product, and how was it different from that? How much was it different? So you need some reference. You cannot just come out with, hey, my parameters are this. Yeah. Yeah.
What kind of projects have you considered? Is it a chip design project, a smartphone design project,
So-
a medical device project,
so-
or a self-driving car project?
So basically, mostly we have focused on software, all the software-related projects. We have done a bunch of hardware as well. So you can basically apply this to anything. So the projects A, B, and C, which I showed over there, they were more of a combination of everything. So you can split it and then say that my software segment is going to have these many defects, or this is how it's going to trend. I mean, you can do that same splitting for your hardware or your firmware or anything else, the IoT or anything. Yes. Yeah. Yeah.
How do you account for technical debt or defects that are found during your project, which may be related to the previous project that were just now been uncovered?
Oh, that's a really good question, and I don't know. Like, if it is for a previous project, then it shouldn't have been like found now when you're releasing the version 2 of it. So, yeah.
Would that just play into your model? I mean, like in our company, that's a constant.
Oh, okay.
Other projects will affect current projects, so that's just the nature of the projects. So I would say that would factor into your historical data. It would be my answer.
Okay. Yes.
One of the traditional ways to do this analysis is with the defect find rate rather than the cumulative defects. Did you try that, and what did you find?
What do you mean by defect find rate?
You map the defect find rate over time, and you see a curve that's going the opposite of your curve, and it has a more visible inflection point.
Okay. So in this case, what we've done is we've also done, so at least I did not show it over here. So we had that SCurve, but we also had a Gaussian as well. So where we are seeing a lot of defects being accumulated at one point. So we did go through over those things, and that was like an added benefit for this. So yes, we did. And this was much more accurate. It was much more visible as well. Like you said, for the inflection point, what happens is if you have a lot of defects clustered around one point, and like I said earlier, for the initial projects, you're going to see lesser number of defects. So that curve is not going to be much more what do you say, fit to that model. So that's why we found the SCurve to be a really good fit. So the inflection point wise, also it's pretty good.
And the second question,
Uh-huh.
can you come up with any reason why this should be an S-curve rather than something else?
Yeah. So, okay. So I had this slide in the backup where we are trying to compare the logistic regression model to many others where you have, say, a cubic function or even, say, logarithmic curves. I don't want to go more into statistical or trigonometry or this thing. So you have like hyperbolic tangents and all. So basically, we wanted more leverage with the variables where the inflection point, asymptote, and this. So this was much more easier to get using just the logistic 3P regression model. So with other models, yes, we did try them, but we didn't have that liberty to vary those slopes and the growth rates and all. So that's a really good question. Yeah. Yes, please.
So you're a little bit depressed when you see that nothing changes, no one learns anything. The next project is that you reproduce the same patterns as before. I mean, is there any hope?
So, yeah. So the thing is that we are implementing this. So the thing is, we know that they are going to ship at that time whether we like it or not. But we want to enforce that. We want to just give them a red alert saying that, see, you're doing this, but you need to understand that, hey, these are the consequences. So just giving them in advance. And many of the teams, not all, so many of the teams that we have gone to across Intel, they have adopted this model. And they were like really curious to know, like, oh, am I doing this? So what should I do now? So just do all these activities. So that is good. So, but it's not widely adopted. Yeah. Yeah.
You mentioned you will apply machine learning on some Python. So what exactly Python you're looking for? It's like for A class, product, B class, product, different curve behavior during the different stage, or?
Okay, so for this thing, how do I say it? You know about SVMs? And yeah, so basically what we did was just a two-dimensional curve. So we just want to go a little bit in higher dimensions and then find out a feature vector and line and then draw more of that. So I'm working on that. So yeah, yeah.
So if I'm reading these correctly, your teams or your management is releasing your product, but only about half of the defects in it have been found. Am I understanding this correctly?
That was just a reference, just an example to show. It was more of an exaggeration, saying that, yeah, it's not something that I'm not saying that, and this is being recorded, right? So that Intel is doing this. So it's just an exaggeration, saying that, hey, this is what happened in those projects. So we don't want to repeat it. Yeah. Yeah.
I have another one. Now you take a past project and you have those parameters, inflection point and growth rate and all that other stuff. And then you take a new project and match it against those, and then you see, for example, I don't know, twice the size of the development team. How does that influence your parameters? Like, do you have like a rule set that says, hey, if this doubles, then you need to notch this up? Or
Yeah, so it's a really good question. So this is still up in the air. Like, we're not quantifying anything. Like I said earlier, like this X amount of increase in developers does not necessarily mean X amount in some bugs or something like that. So this is what we learned through experience by looking at previous projects where we have seen that X amount resembled in that. So we try to apply that and we learn. From there, we say that, hey, this didn't work out that way, so we need to think something against according to that. So what changed? So this is something which is still in my future work, which is in the machine learning side. Yeah. All right. So thank you, everyone. Thank you, especially PNSQC. Yeah. And here's my contact information. So feel free to contact me.